is Team 10, London Aquatic Centre. First, the London Aquatic Centre positioned on the southeastern edge of the Queen's Olympic Park, beside the Olympic Stadium is located. If you look closer at the London Aquatic Centre, water walks river flows, and there is a east-west bridge that connects the river. The pedestrian from the Olympic Park can reach the Aquatic Centre. At the time of the London Olympics, because it should be accommodates 15,700 Olympic athletes from 205 countries and everyday visits by 25 million spectators, the Westfield Shopping Centre is located. Also right side, there is the Stamford Station. Within 500 meter distance can be easily accessible to a stranger. The region's name is the Lower Lea Valley in East London. Its location has a river, commercial space, good accessibility, and daylight because it is positioned southward. But Lower Lea Valley was underserved community with a low-income housing and derelict industrial areas, some of it heavily contaminated. For over 200 years from the Industrial Revolution, a lot of industrial activities had been performed at the Lower Lea Valley. For example, oil refinery, chemical works, cold storage facility, and so on. Among them, there is unusual case, the Hackney Fridge Mountain. The Fridge Mountain is literally refrigerator mountain, because there was an EU regulation that forbid to dump the chemical foam which insulates fridges in landfill. So, the fridges piled up 6,500 for every day until the new regulation is designed. For these reasons, 246 hectares of Queen's Olympic Park is significantly contaminated. So, initial ground investigation and soil reuse was required. Because the London is very crowded traffic, a lot of transport truck can cause city congestion, and finding landfill other sites was difficult. Based on this site-wide remediation strategies, which include soil washing, were implemented. Through the Soil Hospital for 3 years, bring about the present clean and beautiful London Aquatic Centre. From now on, I'm going to talk about the challenges that existed when we built Aquatic Centre. One of the key challenges of the project was developing the structure for the spectator 118,400 feet square waveform roof. It is supported on bearings on two concrete cores 180 feet apart near its northern end and on a concrete wall and its southern end. And it has 118,400 feet square structure spans a column-free area 525 feet long and up to 295 feet wide. The roof contains about 3,200 tons of structural steel, of which 2,000 tons are fabricated plate girders with a structural connection totaling around 600 tons. If so, is it possible that the roof stands without collapsing? The roof structure comprises a series of long span trusses spanning the length of the main pool hull, from a transverse truss mounted on the southern retaining wall bearings to another transverse truss spanning between the northern concrete cores. The main trusses lie in a fan arrangement to create the plane shape of the roof. The center fan trusses cantilever northwards beyond the north transverse truss 100 feet to form an overhanging canopy over the main public entrance plaza. The center fan trusses carry rod in truss section spanning between the north and south transverse trusses, which carry the load down to the supporting bearings on the concrete structure below. Under uniform loading, the two opposite inclined arches in the wing areas balance each other, forming a compression hoop around the roof perimeter. A tension force arises from the change in the geometry of the compression hoop in a plane at the kinks which occur at the wing tips, and this is resisted by a tension tie across the center, and a resulting tension force occurs in the central fan trusses. The structure of the roof can be deduced to a dome form. In a dome structure, at an angle 34 degrees to the normal that separates compression and tensile forces. In the London Aquatic Centre, the angle of the roof is 30 degrees, therefore, it creates a compression hoop instead of tension ring if the angle was greater than 34 degrees. The London Aquatic Centre was designed with long-term community use in mind, and thus both sustainability and cost-effective operation were design priorities. Also, London must meet the ODA's code, so the sustainable design was demanded. Over 150,000 tons of concrete was used in Aquatic Centre. As you know, a lot of CO2 came out in the concrete making process, so they tried to use recycled materials to maximize the sustainability of the concrete. In total, over 80% of the 275,000 tons of aggregates used were from a recycled source. Most of the recycled aggregate was construction and demolition waste from elsewhere in London. As a result, the use of recycled materials on this project saved 4,000 tons of embodied CO2. They also used phthalate-free PVC wrap for flooring. In response to ODA's policy, an innovative flexible phthalate-free PVC was installed at the center. It was the first time this material has been used in this form. Earlier uses of flexible wrap on basketball arena or Olympic Stadium roof used conventional PVC fabric containing phthalate. Also, the design focused on energy efficiency. An ammonia chiller plant provides space cooling and uses rejected heat for pool water heating. This ammonia chiller plant is provided power from a combination of biomass boiler and CCHP plant targeting carbon emissions reduction. The assessment for the Aquatic Centre indicated a marginal global warming benefit of 130 tons of CO2. As the center is for swimming, the water efficiency is important. They achieved 32% reduction in potable water demand. This reduction was equal to 450 megaliters saving in after 25 years. They make this through low-flow fixtures and fittings, low-flow showers and auto-off taps, and low-flow flush was used. Also, they used grey water recycling system to exploit the vast quantities of wastewater. These efforts to make the center more energy efficient made the center more competitive compared to the basic model of the center without concerning sustainability. As you can see in this graph, the difference is quite conspicuous. And this is the end of our presentation. And next week we are going to talk about a foundation, and we have talk about site analysis and challenges this week. And Lee Junsu for team leader research, Ko Jae-sung for PPT design, Shin Sun-woong for research, especially about construction challenge, and Lee Myung-gyu for narration, and Yang Jae-young for site analysis research. Thank you for listening.